Hello, we are FLYFIX Sim4. We'll be presenting automation of road pothole identification and reporting using unmanned aerial system. Our system focuses on detecting potholes using AI from drone capture video and generating GPS tag report to support faster and smarter road maintenance. Our team consists of 4 members, which are Jessie, STACEYLEEN, Alter, and Muhammad ALWI. Now I will present to you the background and objectives. Our project is called Automation of Road Pothole Identification and Reporting using UAS. So we focus on detecting potholes using aerial video recorded by a drone. The drone is operated by payload and navigation team, which captures video and GPS coordination during flight. Our roles is to receive the data through ESP32, process the video using AI and image processing technique, and identify the pothole based on their size and shape. After detecting the potholes, our system estimates their severity and links each one with the GPS location. Then we generate the automated report that can be used by road authorities to plan more efficiently. Our main goals is to provide accurate detection, clear reporting, and to keep the system affordable within a 300 budget. This project is important because it offers a faster, smarter, and more efficient way to monitor road condition, replacing time-consuming manual inspection and helping improve public road safety. This picture here shows what our system output will look like. We just need to add severity and GPS location to complete the report.
The problem statement is, the challenge is that while drone can now capture aerial road imagery, there is often no automated way to extract actionable insights such as pothole size, severity, and location from the raw data video. Our team addressed this gap by developing a lightweight AI-based solution that receives video via ESP32, analyze it to detect potholes and estimate their severity, and generate structured geotech report for road maintenance authorities. So this supports faster decision making, better prioritization, and improve public safety. As we can see in the image, the drone, we get data from the drone, the footage from the drone and then it go to ESP32 cam, and then we extract the data from the ESP32 cam, and then we analyze it using the AI at our laptop.
For stakeholder, the primary stakeholder for the system is JKR Road Maintenance Division, who require a reliable and automated solution for pothole detection and location reporting. The goal is to minimize manual inspection work and reduce road hazard response times. Supporting stakeholders include JKR's IT data team, who handle data integration and reporting. The government can reduce cost and time in road inspection. And lastly, benefit public road user like us, who benefits from improved road safety.
Now presenting the function the design must perform. First, we collect GPS tag aerial video from payload and navigation team via ESP32, then extract video frames and run AI detection to identify the potholes. Third, analyze detected potholes to estimate size and classify the severity. Fourth, attach GPS coordinate to each detected potholes. Then create and export readable reports through PDF for stakeholders like JKR. Then ensure seamless communication between drone, hardware, and detection system. These functions ensure our system achieve its goal of providing accurate, actionable data to support road maintenance. Now the functional block diagram. First, we receive the aerial video data with GPS coordinate from payload and navigation team. This data is sent to our system via ESP32, which acts as the communication bridge. Next, the data enters the image processing unit. This is the heart of our system where the actual AI detection and analysis happen. We begin the processing the video frames to detect any visible potholes using trained AI model. Once the potholes are detected, we analyze them to determine the size and severity. Then, all analyzed data, including size, severity, and GPS location, is then recorded and compiled into structured format for easy reporting. Finally, the system displays the result on the laptop, It shows the pothole's exact location, size, and severity, enabling stakeholders like JKR to act based on the reliable data. Each block represents a modular step that works together to automate pothole detection and reporting efficiently.
Now I will present about the project scope. This project focuses on the development of a lightweight video analysis and reporting system that processes aerial footage capture by a separated payload and navigation module team. The footage, which include GPS coordinate, latitude, and longitude, is transmitted to our system via ESP32. Our group is responsible for receiving this data and detecting pothole using AI-based image analysis, calculate pothole size and severity, and generating structured geotech report to assist maintenance authorities such as JKR. Okay, the scope is create a system that get aerial video and GPS data using ESP32, and then we have to analyze video frame for the pothole and assess their size and severity. Then we have to create a summary report suitable for use by road authorities and then test the system utilizing capture footage in a controlled campus area. And then we have the constraint is the project must be completed within a 14-week academic time frame, and the total development budget is limited to 300. And then we have the problem of the process power of ESP32, and our laptop may be limited to real-time performance, and we have no control over drone flight or video quality as it's provided by an external team. Okay, the assumption is the payload and navigation team will provide clear aerial imagery and synchronized data, and the testing will take place in fair weather and during daytime hours, and users such as maintenance staff require minimal technical literacy to interpret the report. And Wi-Fi and a power supply will be accessible for system use and data transfer, and there is no flight permit are required as drone testing is managed by other team and carried out on university ground.
Component selection, we use ESP32 cam to support onboard image capture and Wi-Fi based data transmission compatible with OpenCV when used with optimization. We also use Raspberry Pi 4 for advanced processing for TensorFlow and OpenCV workload. We also use LiPo battery to power up our ESP32 cam, and a microSD card 16GB for temporary data storage for our footage from the ESP32 data cam. So, for critical software component, we use TensorFlow Lite for HAI model deployment. It was optimized for ESP32 and Raspberry Pi 4. We also use OpenCV Python for real-time image processing and computer vision, and we also use Raspberry Pi OS. It was an OS for Raspberry Pi 4 to compute tasks from the Raspberry Pi 4.
To ensure that the system remains low cost and practicable for governmental use, the FLYFIX project was created with strict budget RM300 total budget cap. Component selection is based on cost-effectiveness, availability, and compatibility with the open source and local infrastructure, and several hardware items are funded or shared through collaboration to reduce direct costs. The following table shows the estimate budget and bills of material, which are divided into hardware and software components. So we estimate that we will use 96% of budget allocated and 4% buffer remaining. So why this budget works? Because we have sponsor item from Sabanet, and we use open source tools like Python and OpenCV. It has zero cost, and we have contingency plan backup drone within our budget. And this will leave RM20 ringgit for unexpected needs while meeting all goals.
Now presenting the roles and responsibility of each member. We plan our roles and responsibility based on each member's strength to ensure a smooth workflow throughout the upcoming project phases. To ensure fairness, we divided the tasks equally. As you can see in the table, each member is assigned two major responsibilities. This way, everyone contributes meaningfully to both technical development and system integration. If we run into delays or technical issues, we are ready to adapt and support each other across tasks. Although the roles are fixed for planning, we also support each other when needed, especially during integration and testing phases. This is our project timeline shown in a Gantt chart, planned over 14 weeks. On week 1 to 3, we begin with Research ESP32, Image Processing and AI Model. During this phase, we also test video transfer and receive sample footage from payload team. All members contribute equally during setup. On week 4 to 8, this is core development phase. We build the image processing pipeline, develop the pothole detection, and implement the size and severity analysis. Alter led the processing and model building, while ALWI handled size and severity. On week 9 to 11, here we integrate GPS coordinates with detection result and test our report generation system for output in format like PDF. I handle GPS integration while Stacey tested report format. The last phase, which are week 12 to 14, here we focus on full system testing, final documentation, and preparation for the final proposal and presentation. All members are involved in this process. Each task is planned to avoid overlap and delay with clear handoff between modules.
Next, verification and evaluation plan. To confirm the system's success, we will evaluate it using a series of functional tests, accuracy benchmark, and field validation. The focus will be on ensuring that detection results match physical potholes condition and that the data handling works as intended. The first one is success metrics: pothole detection accuracy, GPS coordinate correctness, processing speed, and integrity of exported reports. This indicator will be measured against fixed threshold to determine whether the system meets its operational goals. Next, verification tools and methods: OpenCV and Python script for pothole detection, image measurement, and manual comparison and against reference data. Report export will be tested for formatting, completeness, and usability. And lastly, prototype validation. A test video will be recorded over a test area marked with artificial potholes. The drone will fly at known altitude, and the video will be processed offline. If the results exceed the criteria, the system will be deemed functionally complete and ready for presentation. And the table below shows requirement like detect pothole presence, measure pothole size, geotag pothole location, and export pothole report and save local record. And also its verification method with pass criteria. In conclusion, this chapter has shown that the project automation of road pothole identification and reporting using unmanned aerial system (UAS) is both technically and financially achievable. All objectives have been achieved. Our group is focused solely on the pothole detection and reporting module, which possesses GPS tech drone footage from the payload and navigation team. By using an ESP32 based setup and computer vision tools like OpenCV, the system can identify potholes, measure their size, and classify their severity. Be able to generate readable reports for road maintenance teams such as JKR. Testing showed that the system can reach the target accuracy level, making it practical tools for improving road inspection and repair decision.
That's all from us. Thank you.